Welcome back, tech enthusiasts! You know I love breaking down complex topics, making tech more accessible, whether it's the latest smartphone or, in this case, algorithms. Today, we're diving into the top 10 JavaScript algorithms you need to know to ace your next interview. We're talking about the building blocks of efficient code, the kind that makes recruiters hit that contact button. So whether you're a coding newbie or just need a refresher, stick around because we're about to level up your coding game. Let's get started. First up, we have binary search. Imagine looking for a specific book in a library, but instead of checking every single book, you start in the middle. If the book you want is alphabetically before the middle book, you can ignore the entire second half of the library. Binary search is all about dividing the problem in half repeatedly, making it crazy efficient for searching sorted data. We're talking about a time complexity of O log n, which, trust me, is way faster than going through every single element. Think of it this way. Searching through 1,000,000 elements would only take around 20 steps with binary search. This is one of those algorithms that might seem simple on the surface, but understanding its power and how to implement it can really set you apart. Plus, interviewers love to throw curveballs by asking you to optimize code using binary search. Trust me, knowing this one is a must. Next up is merge sort, and this one's all about bringing order to chaos. It's like taking a messy room, dividing it into smaller sections, tidying up each section, and then merging them back together. The beauty of merge sort is its divide and conquer strategy. It breaks down the sorting problem into smaller, more manageable subproblems. This makes it incredibly efficient, especially for larger data sets. We're talking about a consistent time complexity of O log n, which is music to any developer's ears. But here's the thing. Merge sort often uses a bit more memory compared to some other sorting algorithms because it creates new arrays during the merging process. However, that trade-off for speed and consistency makes it a favorite in many scenarios. So yeah, merge sort definitely deserves a spot on our list of must-know algorithms. Quicksort is like the life of the party when it comes to sorting algorithms. It's known for its speed and efficiency, especially in real-world scenarios. The key to quicksort is the pivot. Imagine picking a random element from your data and then arranging everything else around it with smaller elements on one side and larger elements on the other. That's essentially what quicksort does, and it does it recursively until everything is sorted. Now, the time complexity of quicksort can get a bit tricky. In the best and average cases, it also shines with O log n efficiency. But be warned, in the worst case scenario, it can go up to O squared. Don't let that scare you though. With a little bit of clever pivot selection, you can avoid those worst-case scenarios and unleash the true power of quicksort. Chapter 4, Depth First Search, DFS. Exploring the depths. Imagine you're exploring a maze, and you always choose to go as deep down one path as possible before backtracking. That's the essence of Depth First Search, or DFS. It's a graph traversal algorithm that dives deep into a data structure like a tree or a graph, visiting as many nodes as possible along a particular branch before backtracking. DFS is awesome for tasks like finding cycles in graphs, topological sorting, and even solving puzzles with only one solution like mazes. It's relatively straightforward to implement using recursion, and its time complexity is typically O of v plus e, where v is the number of vertices or nodes, and e is the number of edges in the graph. So, if you're dealing with graphs or tree-like structures, DFS is your go-to algorithm. Chapter 5. Breadth First Search, BFS, Level-by-Level Exploration. If DFS is about exploring the depths, Breadth First Search, or BFS, is all about taking a more systematic, level-by-level approach. Think of it like exploring a maze, but this time, you check all the rooms on the same level before moving on to the next. BFS is super useful for finding the shortest path between two nodes in a graph, like finding the shortest route on a map or social networks. It's also used in garbage collection algorithms and even in web crawlers to index web pages. Like DFS, BFS also has a time complexity of O of v plus e, but it explores nodes in a different order. So, depending on your specific problem, one might be more efficient than the other. Knowing both DFS and BFS gives you a versatile toolkit for tackling graph-related challenges. Chapter 6. Dijkstra's Algorithm, the Shortest Path Guru. Ever wondered how GPS apps calculate the fastest route to your destination, even with traffic and road closures? That's where Dijkstra's algorithm comes in. This algorithm is all about finding the shortest path between two nodes in a weighted graph, where weights could represent distances, costs, or any other metric you can think of. Dijkstra's algorithm works by assigning tentative distances to each node and then iteratively updating them until it finds the shortest path to the destination. It's like a smart navigator that always chooses the most efficient route. While the implementation might seem a bit more involved than some other algorithms, the ability to find the shortest path is invaluable in so many applications, from networking to robotics. Chapter 7. Dynamic Programming, the Optimization Wizard. Dynamic programming is like that friend who always remembers the answers to homework problems. It's about solving complex problems by breaking them down into smaller, overlapping sub-problems and storing the solutions to those sub-problems to avoid redundant calculations. It's like having a cheat sheet for your code. One classic example is the Fibonacci sequence. Calculating the nth Fibonacci number can be computationally expensive if you do it recursively. But with dynamic programming, you store the results of previous calculations, so you don't have to redo them every time. This optimization technique can significantly speed up your code, especially for problems with overlapping substructures. So, if you're dealing with optimization problems, dynamic programming is your secret weapon. Chapter 8. Hash Tables, Key Value Powerhouses. Imagine a dictionary where you can instantly look up the definition of any word using its first letter. That's the power of hash tables. They're like super efficient dictionaries for your code. Hash tables use a hash function to map keys to their corresponding values, allowing for incredibly fast insertion, deletion, and retrieval operations. We're talking about an average time complexity of O of 1 for these operations, which is about as fast as it gets. Of course, hash tables have their quirks, like handling collisions when multiple keys map to the same index. But with the right collision resolution strategies, they're an indispensable tool for any developer. Chapter 9. Linked Lists, Data on a Chain. Linked lists are like chains of data where each element points to the next one in line. Unlike arrays, which store data contiguously in memory, linked lists can grow or shrink dynamically, making them super flexible. They're especially useful in situations where you need to insert or delete elements frequently, as these operations can be done in constant time, O of 1, once you've located the position. However, accessing elements in a linked list can be a bit slower than in arrays because you might have to traverse the list from the beginning. Overall, linked lists are a fundamental data structure that every developer should have in their toolkit. Chapter 10. Recursion, the Art of Self-Reference. Recursion is like looking in a mirror that reflects another mirror, creating an infinite reflection. It's about a function calling itself, solving smaller instances of the same problem until it reaches a base case that stops the recursion. It's a powerful technique for solving problems that can be broken down into smaller, self-similar sub-problems, like traversing trees or exploring file systems. Understanding recursion is like unlocking a new level of coding elegance, but it's important to define clear base cases to avoid those infamous Stack Overflow errors. When used wisely, recursion can make your code incredibly concise and expressive. Outro algorithm ace unlocked. That's a wrap on the top 10 JavaScript algorithms for winning interviews. We've covered a lot of ground today, from searching and sorting to graph traversal and dynamic programming. Remember, mastering these algorithms is like leveling up your coding skills. Make sure to practice these and you'll be well on your way to landing that dream job. Don't forget to like, subscribe, and hit the bell icon for more tech tips and tutorials. I'll catch you in the next one. Peace.